All right, thank you. So, listen, thanks very much for the invitation to speak. I really wish I could be there with everybody, but it wasn't to be. But I appreciate the ability, the flexibility in letting me do this talk remotely. I want to do something a little different today. I hope you'll find it, entertaining and interesting. So I'm going to talk a bit about other applications of topology quickly in the beginning. The reason I want to talk about that is I feel that it can give one a guide to what one might try to do in TDA itself. And also at the end, I'm going to subject you to a little bit of philosophy. So anyway, I hope you'll bear with me. Anyway, the question is for me, and I've seen this over the years, how has topology been applied before? So TDA isn't the first application of topology, and I don't mean, outside of mathematics, but perhaps even in mathematics, there are applications of it. So I think it's useful to explore what's been done before. What can we use? What part of the theory from mainstream topology can we use to inform applications? And what aspects from the mainstream are particularly useful? So here is one of the first, an early application of topology, and specifically algebraic topology, the so-called Weil conjectures. So these are conjectures that initially was formulated by Emil Artin. They formulated conjectural formulas for the number of points on curves over a finite field. So here, this is number theory. It's all about enumerating points. For finite fields, it's actually enumerating them. And for non-finite fields, it's about creating kind of proxies that help count points, like L functions and zeta functions. So André Weil proved those conjectures for curves and proposed conjectural formulas for higher dimensional varieties. And he found patterns that are related, interestingly, to the cohomology of the corresponding varieties over the complex numbers. So, I have a variety over the integers, say, defined over the integers. I can ask then for, if I take a finite field, I can ask for counting the points on it. But I can also, with that scheme or the variety over the integers, I can also consider its complex variety. And if I take the points on the complex variety, with suitable structure added to it, it actually gives me formulas for the number of points over the finite field. And so that was the conjecture of Weil. It was proved by Deligne in 1974. Building on the work of others. The key thing here was the Lefschetz fixed point theorem, for this cohomology theory being the key ingredient. Similar questions for curves over the rational numbers is called the section conjecture. So there's a topological version of that as well. Progress is slow on that, the end not in sight, but on the other hand, when proved, it will give an alternate proof to theorems that discuss the number of points over rational points of curves over the rationals. So this is very interesting stuff. And the question is, what's the key tool? So the key tool in here is the homotopy theory over a reference base space. So, and this is a category where you consider not just spaces themselves, but the spaces equipped with a reference map F to some fixed reference base space B. And the morphisms and homotopies are required to respect the reference map. It gives a lot of additional structure. It says that the cohomology of X is a cohomology of B module, and maps respect that structure. And what's nice about that is that it gives many more low-dimensional invariants. When I was first doing TDA and went to talk to other topologists about it, they were all disappointed when they found that 46-dimensional homology is not really something that we deal with in TDA or think about, because it's not computable, frankly. The information in the RIPS complexes and so on is just way too hard to access. You need too many points. But if you can get a lot more low-dimensional invariants that in dimensions 0, 1, 2, and maybe 3, then that's a great win. And so what are these base spaces that I'm talking about, the reference spaces? For the Weil conjectures, for the field FP, it is a space called, it's what's called a profinite version of the circle. It may sound a little exotic here, but it's really, this is something whose homology groups are not, it's like a circle, but the circle, I should say the H1 is Z hat instead, which is the product of the p-adic integers over the different primes. For this section conjecture, it's something called the classifying space of the absolute Galois group of the rationals, which is a huge, very complicated group, very interesting in its own right because it contains so much arithmetic information. Anyway, for a curve V over Q, there's a space like this called, VQ to be BGQ. And the rational points are conjectured to be in bijective correspondence with sections of this map. Okay, and there's a lot of evidence for it, but as I said, there's progress, but we're not close to making it into a tool the way the Weil conjectures are. So what I want to say now is I want to ask, can we take this philosophy and can we make some use of it in TDA, in topological data science or topological data analysis? So what I'm going to describe here is a little bit of work of Brad Nelson, who was a student of mine a few years ago. So, one of the early demonstrations of the value of persistent homology was this Mumford image patch data set, something that we studied, we got the homology out of it and so on. Ultimately, the finding was that the frequently occurring image patches concentrated around a Klein bottle. But looking back, obtaining that finding was very painful because, in order to get something which is expected to model correctly the space underneath, you had to filter somehow by density. And it turned out that the density actually varied a great deal from region to region in the space. And I'll talk exactly about how that was. Yeah, and it turns out that it varied a great deal, but systematically. So the finding can be made much more direct and immediate with data science over a base. And I'll explain that. So in particular, varying notions of density over the fibers of the map are important, or fibers of a map are important. So just to make it concrete here, first of all, here is a Klein bottle. This is the space with identifications made around both sides. And this is the parameterization of the image patches by the Klein bottle. And we had this particular part we called the primary circle, which is the red there. Notice that you've got two red lines, but they really join. So the lower right red line corner is connected with the upper left and so on. That was called the primary circle, and that consists of basically the edge detectors. On the other hand, there's a lot of secondary circles, two of them in particular, one with the vertical and one with the horizontal. But it turned out that, even on that primary circle, the density varied a great deal. So the density for the vertical and horizontal ones was quite high. And then as you got to something which was more at a 45-degree angle, the density was low. And that made it hard to do the filtering correctly. So anyway, as I said, the first analysis showed that the directionality or angle of the patch is important and that the density varied in a predictable way. So what I want to do now is I want to take this directionality, and this is what Brad did. He was able to say, look, we do a quick analysis which does not involve this Klein bottle at all. We find that there is a primary circle. This involves heavy thresholding by density, and it's a one-dimensional space. And this directionality can be viewed now as a feature of the data set. So take my data set now via an edge detector to be a space, a data set, but with a reference map to the circle. So we now have a data set over the base circle. And what this means is now that we realize that, we can also see that the density varies on the circle. And so what we'll now do is we'll compute the homology of the fibers over various points. That's because it's a fibration here. You can say for each circle, for each point, I should say, on this primary circle, I can see the inverse image being one of those secondary circles. But the key point here is that you have to do the density estimated fiber-wise, so that you'll compute at the points at the ones that are at an angle of 45 degrees. In each fiber there, you select points based on the percentage density threshold in that fiber. So that takes away, that problem of having the density, the density vary. And it also makes the homology easier to compute because I can, once I've got it broken up as a map like this, I can use a spectral sequence if I want to be very technical, or just realize that, I can take a covering of that base space and then compute the homology of the inverse image of those elements in that covering. So it makes the computations easier. I don't have to go directly at H2, but I can do this fiber-wise thing. So here's the picture of the Klein bottle as a fibration over the circle. So after this fiber-wise density filtration has been applied, and then one performs the homology computation, the computation comes out directly without fiddling. And when I say fiddling, I mean the kind of fiddling that we had to do to get that right answer out of the data set, where we didn't realize that it was being treated as a map as a space over the circle. And again, because of tools of local to global analysis, one also simplifies the homology calculations. So we kind of believe that that this is an example where the correct structure is as a space with filtration over a base with a filtration. And so ultimately, we believe that this view of taking things over a base, should be useful in other situations where you have complex things which can be, either by analysis or by understanding that they come with reference maps to some interesting space. Okay, so now just very quickly, another, application of topology, and I apologize, this is, still in topology perhaps, but it is the homeomorphism classification of manifolds. So, ordinary homology doesn't see the difference between Rm and Rn, when M are different from N. They're homotopy equivalent, but not homeomorphic. But surgery theory has been developed to address this difference. And it has worked very well for large classes of manifolds. And what we call coarse homotopy theory is part of the solution. So what's coarse homotopy theory? I'm going to just describe it to you in a fuzzy way here. It sees only infinite behavior. So one of the properties of it is, for example, that the map from the integers into the real numbers is a coarse equivalence. So what it does is it tracks compactifications at infinity, asymptotic behavior, and erases all kind of local behavior. That's what's meant by the coarseness. And that has some, relationship, I think, to what we think about with data. Obviously, we don't apply it directly like this because we don't have infinite things, but perhaps, analogs are useful. I will say that this is how I first got into the whole TDA business, was in working in this area and, running into the Vittorius-Rips complex from this point of view before thinking about it as data. In any case, there's been formal schemes developed now where one can do homotopy theory in various contexts. They're called Quillen model categories, and there's something even more, modern, which are called infinity categories due to Jacob Lurie. So things we do in applied topology, perhaps they can be thought of in those terms. Anyway, just finally on this, the key point here in these things becomes the abstraction of a notion of covering, and the constructions of covering is key in these applications, just as it is for us in TDA. So there's a concept called the Grothendieck topology on a category, generalizes the notion of a topology on a space, and a site is a category equipped with such a topology, and a topos is a category of sheaves on a site. To give you a sense of it, if you look on the right there, one of the things that has to be added in there as a covering is a covering space. This is something in a number theoretic context, at least, one has to add that as a notion of a covering as well, in order to get that to work out correctly. Anyway, permits the construction of inverse systems of nerves of simplicial or coverings, which are the analog of spaces for number theory. Okay, so now I want to talk about TDA, coverings for TDA. And so what obviously we use a lot of them. Many constructions of coverings, check constructions are kind of very generic thing that one can do. Vittorius Rips is not strictly covering based, more relational, but maybe it fits in here as well. And alpha complexes due to Herbert Adelsbrunner, and then Mapper and its variants. So what I'm going to do now is I'm going to talk a little bit about alpha complexes, where there's been some interesting work done recently. And then I'm going to move to Mapper and its variants and sort of ask the questions of what capabilities should we have for Mapper? Okay, so the alpha complexes, first there's the Voronoi diagram and Delaunay triangulation. So here, the Voronoi diagram, as you probably know, if I have a set of points in Euclidean space, for each point, this Voronoi cell around that point is a set of points which are closer to that point than to any other point in the subset. So that's a diagram. It gives a covering of the Euclidean space, or in this case. The Delaunay triangulation then is the nerve of the covering of Euclidean space by Voronoi cells. And so alpha complexes are sort of the version of that I do when I can threshold by a radius. So where I will only include intersections of balls of certain radius with those cells in the covering. So the alpha complexes are much smaller than Check or Rips constructions. They produce coverings, but they're a little bit agnostic to the shape of sets in the covering. So they're not restricted to balls as in the Check construction, but they can even change in size and change in shape, which is additional flexibility. So direct constructions of the alpha complex are very computationally expensive. They typically proceed by doing divide and conquer methodologies based on cutting up your Euclidean space into pieces. And they are impractical in even moderately high dimensions, for example, 10. So there's been work by Eric and Gunnar Carlsson circumventing these problems in this paper that I'm describing below, and I'm going to give you the rough high-level description of that work. So again, the alpha complexes, we denote the Voronoi cells for a subset of Rn are given by V sub xi, but for a given radius and point x, the radius restricted Voronoi cell is the intersection of Vx with the ball of radius R of x. So the nerve of this covering by the sets VR of x is called the restricted alpha complex, and it is not a triangulation of the Euclidean space. It is a triangulation of something smaller, and so can carry interesting topology. Is not in general contractible. So how do you determine if sigma, a set of points x naught to xl, contained in S? So S is a set inside a Euclidean space if it spans a simplex in the R-restricted complex. Well, it turns out that what that amounts to is solving a constrained quadratic optimization problem. So you can see there, look, you're asking, I'm going to minimize the distance from y, so a vector, y is the variable that's being minimized, and you're minimizing the distance from that to a point x. So I'm talking about a particular point x in S, subject to the constraints that y minus xi is less than or equal to y minus xj. So that's the where xi is in sigma and xj is in S minus sigma. So that's the condition that I have my point be closer to the xi's in sigma than to any other points. And then the second condition then is the one that says that, the distance from y to the points within the simplex are identical, which is saying that, in fact, it lies, it's the intersection of those Voronoi cells. So if I solve this constrained quadratic optimization problem and find that the minimizer is less than R squared, then I conclude that this is indeed a simplex. So, and the constraints can be made linear by squaring and canceling quadratic terms. Okay, so this is the constrained quadratic optimization problem, but what it means is that I have to solve a quadratic optimization problem for every for every simplex and every subset here, and it's a long list. And the fact that that list is so long is what makes it quite infeasible to compute. And the point here is what you can see is that here I could consider the number of variables, the dimension of the problem, but the optimization here sort of there's one for every constraint here. There's a very large number of constraints because you can see the constraints they have to do with basically all pairs xi and xj in my data set. So what these guys do, they take this point of view. They say, look, typical linear programming problem is this. It says minimize CT times X subject to these linear constraints, inequalities. Okay. Now, in that theory, there's a dual problem, which is defined the way I've written it down here. So it's maximize BTY subject to AT, A transpose of Y equals C, and Y is greater than or equal to 0. Now, so the theorem about this duality in linear programming, and in fact, it applies to quadratic programming as well, is that the solutions here are identical. So in other words, if the primal problem, so that's the first one, the initial problem, has m variables and n constraints, the dual problem has n variables and m constraints. So, and as I say, this applies to quadratic programming. So the trick in this paper that I described is to solve the dual problem. So again, for a data set with capital N points and lowercase n variables, the alpha complex optimization problem has little n variables and roughly n constraints. Actually n squared constraints, I think. So anyway, the dual problem, for a fixed simplex, it's n constraints. The dual problem has, on the other hand, a lot of variables, capital N variables, but lowercase n constraints. So for this problem, the number of constraints turns out to be the main driver of computational complexity. And so using this dual problem permits calculations of the alpha complex in higher dimensions than has been accomplished before, at least to their knowledge. So, and just as an illustrative example, is it constructed a data set of configurations in 4 points in R2. So, this is 4 tuples of distinct points in R2 related to hard disks. And again, the subspace, that's a non-compact subspace. You don't want to be involved in that. So they actually built a compact subspace in there, which is included in there, but it's not necessarily exactly the configuration space. It's more closely related to the space of hard disks. So, this subset, though, is in 8 dimensions. And so here, just for comparison, they ran RIPSER on it, found that RIPSER could compute Betty 1 and 2 in 40 minutes, but was unable to compute Betty 3. And this alpha complex was able to compute, all 4 of the Betty numbers, and to do so in 4 minutes. Okay. So what I want to do now is I want to start to understand kind of mapper and other complex constructions. Actually, everything I'm talking about here is applicable to other complex constructors as well. But I want to understand what capabilities do we want to add to those to mapper? What capabilities do we want mapper to have in order to make it maximally useful? So let me remind you, first of all, about mapper itself. You apply projection to the data set. You use the projection of the data set to create overlapping bins. You cluster each bin using some fixed clustering method. Create a node for each one of these partial clusters. So we've got okay, sorry. There. Yeah, and so we get this situation right here, where what we've done is, in this case, and this is, of course, the perfect situation. It's never quite as nice as this, but nevertheless, it creates a covering, which in this case shows you that you actually retain that circular structure or loopy structure, at least in this case with a hexagon. So the mapper is an analog of a read graph. It requires a choice of one or more filter functions. It's both a good and a bad thing. Sometimes you're really interested in the filter functions. Other times you would like something where you're not required to choose that. So it's often useful in situations where one wants to encode a priori structure of the data. There's a very nice version of a mapper which does not use filters and is more closely related to a Czech style construction due to Pavel. And here's a picture of its application to data from COVID. It's like a check complex doesn't produce filter functions, and it does produce a persistent complex as well. So this is something that one could equally well use. And then there's also a multi-scale mapper due to Tamal, Facundo Memoli, and Yusu Wang, which studies mapper for different covers of the reference space. So mapper itself, of course, is requiring a reference target space. So in a sense, we could think of that as a reuse of that philosophy of understanding a space with reference map to a base. And it combines mapper and persistent homology to analyze stability. One of the things about mapper is that it's useful to find stuff, certainly, but there also needs to be, and people are working on that, including this work, about ways to analyze the stability of a mapper with persistent homology. But now the question becomes, so what do we want from these complexes? Well, the very first thing is we probably want unsupervised methods just for understanding your data. So just as an example here, this is one that was done quite some time ago, some 10 years ago, where you find this is a data set of type 2 diabetic patients who have genomic data as well as healthcare record data. And they found, the Joel Dudley group at Mount Sinai found that, yeah, you can use this to create this mapper graph here. And what they found was from that immediately an understanding that there are really 3 types of diabetes, which they later promoted to 4, but that there are some, perhaps degree of overlap between them. So this kind of thing, stratifying diseases, is fundamentally important because oftentimes your treatments will depend on that. So if I have to produce a treatment for all of diabetics all at once, that's much harder than taking it and producing it for each of these groups individually. Something else we might want to do, though, is to have query capability for subgroups and quantities, variables on the data. So here is an example which many of you may have seen before. This is intensive care unit patients. The data set is questionnaires filled out by the personnel in the intensive care unit. And the machine learning predictor was built to predict survival, which you can see in the upper left, the mapper diagram is colored by that. And on the lower right, it's colored instead by the actual survival. So you can kind of audit this model. And one thing that you can see here is that there's a group where, the predicted survival is really very good, but in fact, they almost all died. And you can quickly go in and kind of do forensics on this, if you like, model forensics, and find out that, that group of red people there, that's where people did not fill out large chunks of the, of the questionnaires. So that's something good that you can do now. You can now modify your model to take that into account, or just simply say, if you're in this, if you don't have those questions answered, this model's not reliable. Another thing that we might want to do for complexes is to analyze features for wide data sets. So wide data sets would be data sets with a lot of features, like one gets in genomics, for example, where you might measure expression levels for hundreds or thousands of genes. And so here is an example of this, just to sort of show that it works. This is a gut biome data set from UC San Diego, where the features are bacterial subpopulations, and this is a space of those based on those on the the frequencies or the abundances of those things for the large collection of patients. So the graph model is again of the features, the populations, not the patients. And what you can see is that in the lower right, which is the healthy group, I believe. No, the ulcerative colitis group is on the right. You can compare that with the healthy group on the left. You can see that there's a large red group that's circled in the lower right that is simply not present in the healthy patients. And this says that in these situations where we have sort of wide data sets with very large feature sets, oftentimes what we have is that it's not a single feature that's doing it. In fact, it's not even one or two. It's actually large collections of features that are acting in concert. And those are the sort of things that you can discover with topology here. And similarly, you can compare to Crohn's disease, which is the upper right, where what you see is that there's actually a red group that's at the very top that's circled on the left, which is missing in the Crohn's patients. Another thing that we might want from these complexes and that we might want to do when we're doing any kind of data analysis is we want to understand ways of generating features. So I'm going to just show you one example of this. This is for so-called ductal carcinoma in situ. It is a breast tumor, which often is kind of benign or not very serious, but which sometimes progresses to more serious disease. So what we have was a single cell data set, so an analysis of the cells from patients with this DCIS, the ductal carcinoma in situ. And it's imaged by a particular Mibitov imaging technology by the Mike Angelo group at Stanford. So we constructed a mapper model of all the cells. And so each patient then produces a function on the vertices of this graph, right? Because if I can take the abundance of cells from that patient within a particular node of the graph and color by that. So and it turns out to be extremely informative about progression from mild disease to more serious. So let me show you. Yeah. So this is the graph of all the cells. And now if I take the cells that come from patients, so this is a retrospective study, so they knew who progressed. And so I can take progressors and I can, color each node by the number of, cells in there that came from progressors. So what you can see is that there's a very heavy red in that upper left-hand corner. What's interesting, though, is that this captures very nicely not only the progressors, but the fact that there's two different kinds of progressors. One from HER2, which is a one type of cancer, one type of tumor, versus luminal B. And you can see there, those two together make up all the progressors. And furthermore, they are distinct. It's distinct cell types that occur. And then finally, the interesting finding here was that really what this was reflecting is the sodium plus ion abundance within within these cells. So these were very interesting findings in our opinion. The main thing to think about here is that oftentimes what's done in single cell studies is that you have beforehand you've decided to divide up your cells into a number of classes. And then measure the quantities, the percentages of cells in each of those classes. And this is doing that also, but it's breaking them into a lot of classes and recognizing that they relate to each other, they fit together into a graph structure, and that gives you the more power to it here. Yeah. What's another thing that we might want from these complexes? So we want feature generation. We might want feature engineering as well. And so this is, sort of a related study to the one that I just showed you. This is joint work with some other people at UCSD. Um, and this is on studying so-called luminal B breast cancer. We're not in the DCIS domain anymore, but it turns out there had been a suspicion that one of the groups in the current taxonomy, so it includes luminal A, luminal B, HER2, and triple negative. That's a reasonable taxonomy, but there had been a feeling that this luminal B group should break up into pieces. And so what was done here by the lead author here, who's Zara Rostani, she used both this feature space because this is a genomic data set, so it's got a large feature set, and she basically worked with it in the way that we do, selected groups back and forth and did kind of hands-on feature engineering until we arrived at the fact that, yeah, indeed, that the luminal B is really two groups, and furthermore was able to then get particular features that when you projected on them, it made those distinctions clear. Okay. So now the final one I want to talk about is double mapper. Okay, so I think this is very interesting. So double mapper is where you have a data set which has both a reasonably large number of data points and a large number of features, so that you can build a mapper graph both of the sample points and the and the features. So I'm just going to show you here double mapper in action. So on the left here is the data points. This is a genomic study of a certain kind. And so I'm able to select points on the data points and see how they color that feature space. So and bear with me here. You can see there's some good differentiation going on here. You can see quite a bit of what's happening. In the lower right there, you're getting heavy coloration. And then in here, this thing, and look at that group on the right, which is kind of, red and yellow up at the top. That looks interesting. It's sort of shown up a couple of times. So now we're going to take this thing, and so when I take that one, you see I get this very sharply well-defined group in the patient space. And let's look at doing that. And you get, a different, very well-defined group, different group, and another group there, and yeah. So what I found very interesting about this, is it looks to me like the differentiation is very much sharper when I go from the feature space. When I make selections in the feature space, I get very sharply defined areas inside my samples. On the other hand, when I choose the samples, I get something, but it's not nearly as well defined as in the feature space. And one of the things that I'm wondering about, and I don't have answers to this, but it's a question I'm kind of putting out there, is what's the explanation for this? Is there something about the data set, something characteristic of the data set, which accounts for this difference as I go from, the feature space selection in there produces so much sharper things than the feature space selection in the left. But my view is that this thing here is something which one could do to any data set, and which is provided it's wide enough that it's got enough features to it, and so it's a better invariant than either one of them individually because it's very searchable. Okay. So, okay, I want to take another step here. I want to think about some particular projects that we've been doing. So, of course, large language models are extremely, popular and interesting now. Certainly in my neck of the woods out here in Silicon Valley, but I think around the world. So LLMs, large language models, are a huge part of AI now. Maybe they're the most important part of AI. It's certainly, as far as the news goes, it is. But they really are not very well understood. In fact, I think there's only just now is there a consensus developing around a notion called mechanistic interpretability that says that indeed it's going to be important and useful to understand what these things are doing. So how can we start to understand them? And maybe more to the point than, well, or maybe one way to think about that is how can we do signal processing and feature engineering for them? Are there ways to create new features, interesting features that can be fed into such models? Anyway, the main point is that what they do is the methods, these large language models, are built off the so-called transformer model methodology here. And what they do is they transform sequences of words into other sequences of words. So, for example, originally one of these things called BERT was built to perform machine translation. But now what they're doing is they're finding that you can start, if you ask the questions the right way, you get good answers from this, or reasonably good answers, just out of taking optimizing for predicting the next word in a sequence based on the preceding sequence. So within these models, there's a so-called attention mechanism, which allows the possibility of considering the effects of words far back in the sequence to the next one. The miracle is that this optimization combined with prompt engineering, which is this, choosing your inputs correctly, allows the LLM to answer questions very effectively. So, but there are still problems. They hallucinate. If you start asking them serious math questions, they have problems. You may have tried this. I certainly have. So I want to just produce, I want to tell you about one little experiment that we've done, a small experiment here. So it should not be thought of as conclusive in any sense, but it's indicative. So one of the things that you can do, if I take all the words in English or in any language, I can, of course, consider the parts of speech in that language. So every actual sentence can then be reduced to a sequence of parts of speech with so-called parts of speech tagging. And so we call these sequences POS sentences. And I'm going to ignore the fact here that some words can be more than one part of speech. That it's something that is true and that one can handle. So anyway, what one can then do is one can take this toy version here, these so-called POS sentences, and build a small transformer to predict the next part of speech, having seen a sequence of parts of speech. So the embeddings produced this way can be made very small, like 10 dimensions instead of sort of, several hundred dimensions, which is often what's being used. And so just to give you the sense of it, the POS sentences are, the sentence, the black cat caught the mouse. That corresponds to this sentence, which is article, adjective, noun, verb, article, and noun. So this lower. So what you can then do is you can train a neural net for that, and you get to something like 45 or 50% accuracy in predicting the next part of speech. But what's very interesting is that you get some very simple features then, or small features, like 10 dimensions, 10 of them, on a set of POS sentences. And you can concatenate these features with the actual sentence embedding, with the much larger sentence embedding, and fine-tune the model suitably, or tune it where it's being given a priori this kind of part of speech information. And so what we did is we obtained then 15% improvement in so-called perplexity. So perplexity is a measure of the degree of confusion of the networks and the transformers, the degree of uncertainty in predicting the next word. And the modified transformer architecture for this, I'm just giving you you can see that the tokens and the token embeddings on the left go into, as they would in an ordinary transformer, whereas on the right, I have these POS features. I add them in and I concatenate them. And then I do a generic linear projection, which is trained, or learned, I should say. That projection is what's being learned to adapt the model, and then you proceed. So this is what was done there. What was interesting though is we said, well, maybe these part of speech features can be more interpretable. They're smaller, so maybe there's a chance to see them. And so what we did is we took the embeddings that we got, the 10-dimensional embedding. When you look at it first, you realize that length is a big driver here. So if you don't do something about that, you're not going to get a good network. Ultimately, I think the right thing is to build a mapper model with the length as a filter. But what we decided to do here, just for simplicity, was to take the middle quantile of length and build just a straight up, mapper construction on that. And you can see here two of the groups here that and here what was interesting was what we did. We took then the sentences, the actual sentences that corresponded to parts of speech sentences in these groups, and asked an LLM to tell us the difference between what characterized that set of sentences and what characterized the difference between the two groups. And so the LLM came up with several things, but just, one of them was that the thing on the left is sort of straightforward narrative sequencing, whereas the thing on the right is what's sort of called expository compression. So you can read those, an example of that here on the right. So this is very early days on this. I really think this is quite interesting. It will correspond to what I would say is syntactic instead of semantic features on sentences. So now here's a generalization, and it's just an approach to the study of transformers acting on all data sets of sequences, such as text. So in the case of text, maybe it's viewed as sequences of words or sequences of tokens. But suppose that I can construct maps from my vocabulary to much smaller sets or much smaller vocabularies, and then predict elements in those sequences. Well, just like we did with parts of speech here, any kind of reduction like that produces a smaller model, which one A could find perhaps interpretable, and then B also hope to gain improvement by concatenating it with the input. So the next on the agenda for us on this is to use WordNet or other thesaurus-like assets to divide words into high-level groups or concepts. So, for example, dogs, cats, and giraffes would belong inside animal, inside the group or concept of animal. And so we want to build a transformer to predict the next concept in a concept sequence. So ideally where I'd like to go with that is to get it down to where we've got 500 or 1,000 concepts, and then perform the same kind of analysis on it, see what kind of next concept prediction we can get, and then feed it in and see how it can help the network. I would also say that it's a huge thing right now, the whole idea of adapting a large language model, adapting it to be useful for a specific case. So I mentioned to, and you probably are aware, that if you ask mathematical questions, you often don't get the right answers. Well, same is true of any specialized vocabulary. And so particularly for those vocabularies, this kind of thing is, this kind of feature generation, or signal processing, as I call it, is something that one wants to do in adapting those large language models to specific tasks. Okay, where am I doing on time here? Okay, I'm doing it. All right, convolutional neural networks. So, convolutional neural networks were, I think, the big success that really has put, AI on the map again in a very serious way. They, performed all sorts of image classification problems. They solved many of those. And, the key point here was that it made a restriction on the architecture and on the and also on the weights of a neural network. So, the architecture is built in such a way that I'm keeping track of the fact that an image is actually a rectangular array. And I'm also insisting that, the weights at a particular point in one of these square arrays should all be they should all be the same as the points at other parts of it. So, that the computation recognizes that a dog is a dog, whether it's in one part of and it does so in the same way in the different parts of the network. So you can take one of these networks and now you can ask, well, which filters are being computed there? Because the filters are simply for each node, I take the 9 nodes or the 9 pixels from the preceding layer that feed into it. And so what I get is an analysis of, sort of 3 by 3 arrays of numbers. Those are weights, but they can be thought of, it turns out, as as image patches, like we thought of at the very beginning on this Klein model. And so what this shows, this is a mapper diagram showing what happens here, and you find that this is recapitulating the primary circle. So in other words, and this is a very small neural net here, but it appears to be it's the similar thing that we first found in studying image patches. And the same way with CFAR 10, which is a more complicated data set with 10 classes. Here, this is, I think, is the second or third layer. You see, you have the primary circle sitting on the outside, but then you also have something here which did not appear in the Klein model even. This is kind of a bullseye, a white bullseye in the middle of a black region. So here's a description of VGG16 on ImageNet. So VGG16 is a large neural network that was trained on ImageNet and that did remarkable things. ImageNet has 1,000 classes, not just 10. And what this illustrates is the behavior of the various layers. What are the responsibilities of the layers? And so what you can see is that layers 1 and 2 perform only, basically primary circle edge detectors. But then you can see 3 and 4 start to get more stuff going on. So in set 3 there, for example, those are some secondary circles, in the horizontal direction. You can see also in layer 5 that, what you see there is a crossing, which is a non-Klein model filter. So those get used, but they get used at the higher levels where one is expecting, because of pooling and things like that you are seeing more large-scale features. Anyway, this gives a way of clarifying what the responsibilities of the various layers are. What we also found interesting, though, was that we were able to also analyze the learning process. So, as you're learning this thing, as the neural nets perform by optimization, and they do so with iterations. And so, in this case, this is a very small neural network, trained on CFAR as well, I believe, but only a 2-layer network. And so, and then you can see the lower line there indicates how many iterations have been done in the optimization at that given point. So what you can see here is that the first layer quickly starts to organize itself into a circle. So these are mapper pictures. You'll notice that some of them, they're carpets, but they're colored by the number of elements in there. So you should really think of that second one from the left on the top there. That's really starting to be a circle, because the middle is pretty sparse, whereas the circle is dense. And it gets even better. It actually produces a circle at the 3rd stage. So, all right, so that's good. That's what we expected. But what we didn't expect to see was that after that point, as you get to the 4th and 5th layer, that primary circle starts to degrade. And so it's actually falling apart. You're continuing to get, the pieces that go in the, in the vertical and horizontal directions, but and then something in the middle there, but you're not retaining that entire circle. So now what happens then with the second layer, you'll notice that almost nothing is happening in this learning process through 100, 200, 400, and 500 iterations. But at 900 iterations, it's starting to organize itself into a primary circle, which is compensating for the failure of, or for the fact that that first layer is degrading. And so by the time you get to 2,000 iterations, you can see that you've got, the full circle there, at the second layer. Now, we don't believe that this is, related to anything that really happens in human or mammalian or other animal visual cortexes. We don't believe that. But what we believe is that this is too shallow a network to do the job in the way that you expect it, and so it's doing it in some kludgy way, which is making the second layer into the primary circle. What we found really interesting, though, was that we were able um, to actually start and get in and improve convolutional neural networks. So what I've just shown you is some insights into it. What we have now said is let's embed the Klein bottle. Let's go ahead and make the Klein bottle into new features, which we inject in there, and we also even modify the architectures a bit. So we feed those to the neural network at the starting point. So this kind of feature injection and modified architectures, which is what I'm describing there, they provide an improvement in learning time, which is obvious because, of course, if the network has to learn, those edge detectors, if you feed them edge detectors right away, they can get busy on doing other things, and so they learn much more quickly. That's not a big deal. But what the huge improvement, we got a huge improvement in generalization. So generalization means, that you can train a network, train a neural network on one data set and evaluate it on another. And the ability to do that is called generalization. And I kind of believe that it's the key ingredient, the key metric for thinking about how do you get to what's called AGI, the generalized, artificial generalized intelligence. And you can see here all those curves. So the experiment here was to, first of all, take MNIST, noise it up, and then train on the noisy data set, and then attempt to evaluate on the clean one. And so what you see there is the green, orange, purple, and red things are all different variants on this Klein modified network. So some of them involve just the primary circle and others involve the Klein circle, and there's other modifications as well. And then the bottom line is an ordinary convolutional neural net. And what you can see is it never gets there. In other words, for this data set, it doesn't produce something that's generalizable in any reasonable way. Because it's overfitting on some features coming from MNIST. And as you can see on the right there, the other one is where we had it's a noisy test set, so we trained on the clean one. And you can see again the performance in accuracy is again dramatically improved with these modified networks. Okay. All right. So I warned you that I would try to talk a little bit of philosophy at the end, so I will do that, and hope you bear with me. So database theory distinguishes between intentional and extensional sets. So what is that? Intentional sets are things that, the points x and y, so that x is less than 0 and the y plus x is greater than 2, or equalities and inequalities among variables. They are the sets that you can get by restricting things in an algebraic fashion. But extensional sets are sets defined only by enumeration with no particular formal description. So this is often what one, what one wants or what one is looking for in genomic studies, for example, but many others. And so standard data science and mathematics deals well with intentional sets. And what these TDA complexes, and all of them have this property, if they're good representations of the data set, allow users to deal effectively and systematically with extensional sets by performing selections, taking particular extensional sets and coloring by them and so on. It gives the tool suite for working with extensional sets to extend, kind of data science beyond algebra. And so now I want to just, invite you to think with me about this. So think about foundations here. So Hausdorff invented topological spaces in 1914. He recognized that by encoding the notion of spaces, so by algebras of subsets, so rather than viewing them as sets of as solutions to sets of equations, he said, look, it's better to think about spaces as algebras of these open subsets, and that gave a flexibility that was not present in the view of spaces as defined by equations and inequalities. Oftentimes, the equations and inequalities would obscure the properties of the space that come simply and directly out of this view of his. So social scientist, mathematician, R.H. Atkin proposed simplicial complex models for social sciences in 1977, um, where he recognized the notion of a covering or a soft clustering or a weak clustering of coverings are key in there. And so coverings are of course sort of key to the notion of topological spaces as well. So, so what I propose here at the end is maybe for topological data science, rather than open sets, one should somehow work and define what one means by notions of sort of explainable extensional sets or kind of reasonable extensional sets to be the analog of open sets. Maybe they're sort of characterized by some kind of entropy. I don't know. Anyway, I warned you this would be philosophical, and I'm just putting it out there. And that finishes the talk. So I thank you for your attention.